Hi guys, this is Amit Kaudairana and this is my project for data management. I have built a entire data pipeline for Germany's EV charging infrastructure. I took the data from 3 different data sources. I cleaned it, transformed it and loaded back into the cloud data warehouse. So finally it produces a 4 key metrics that which is used to solve the one key business problem. So now let's dive into the presentation. So let me start with the problem I'm solving. Germany is one of the fastest growing EV markets in Europe right now. Every year, more people are buying electric cars, but the charging stations are just not growing at the same speed. And the real issue was nobody had one signal system giving a clear answer to this. Which specific areas in Germany have too many electric vehicles but not enough chargers? There was no real time data, no combined view. Charging operators and city planners were basically working blind. These 6 main cities of Germany, namely Hamburg, Berlin, Frankfurt, Munich, Cologne, and Stuttgart. These are the cities this pipeline is mainly covering. To solve this, I built one pipeline that pulls from 3 completely different data sources. First one is the TomTom Live API. So this is the fast moving data. So every 30 minutes, it is giving me a real time plug status of every charging station. How many are available, occupied, whether it's broken. So it gives the data in the format of JSON. So and the second data source is BNetzA registry. So this is a slow moving data. It is Germany's official government database, so of every physically installed charger in the country. Comes quarterly. It is simple CSV format. And the third one is the KBA vehicle data. This is the medium speed data. EV registrations per distinct across the Germany. So and this is updated annually, and this is in GeoJSON format from the ArcGIS website. So 3 sources, 3 different speeds, but 3 completely different formats. So by joining all the 3 together, so the pipeline calculates one main output, the demand gap score, which tells you exactly which postal zones are under the most pressure. So coming into the technologies that I used and what's the main reason behind of the each choice. So first one is the Apache Airflow. So this is mainly used for scheduling the orchestration, and it runs the pipeline automatically, manages which task runs after which, and handles failures properly. PySpark for the data ingestion. So the current data volume is small, but I use the PySpark so that when the pipeline scales to all of the Germany, I do not need to rewrite anything. And another one is the Google BigQuery. As the cloud data warehouse serverless scalable, no infrastructure to manage. And also the another one which I used is a DBT core that is mainly used for the transformation layers and data quality testing. So it keeps the code clean, testable, and easy to maintain. And also Google Cloud Storage as the staging zone where raw files land before going to BigQuery, and finally a Tableau for the final dashboard. This is how data flows through the system from start to the finish. 3 sources on the left feed into PySpark. PySpark extracts the data, flattens it into proper table format, and puts the output files into a cloud storage, a bucket. BigQuery then picks it up from the cloud storage and loads it into the warehouse. So inside the BigQuery, the data moves through 3 layers. This pattern is called as medallion architecture. Bronze is where the raw data lands. Nothing here is touched. It is kept exactly as it came from the data sources. Silver is where DBT does all the cleaning, fixing, and final layer is called as the gold layer, where data is fully transformed. All 4 metrics are calculated here and ready to use. So 3 layers as a 3 clear jobs. Raw data goes in one end, clean business ready numbers come out the other end. So yeah, let me go a bit deeper into each layer. Bronze layer has 3 raw tables, one for each source. Raw live occupancy from TomTom, raw BNetzA registry from BNetzA, and raw KBA demand from KBA. So data here is append only, meaning nothing is ever deleted or overwritten. So you always have the full history of every pipeline run since day one. Silver layer is where DBT is doing all the cleaning work. All the issues I found when I first looked at the raw data are getting fixed here. And finally the gold layer as one final table, mart demand gap analysis, where all three sources are joined and all four business metrics are computed and ready. So these are the four metrics the pipeline is producing automatically. First one is the utilization rate. This simply tells how busy a charging station is right now. Demand gap score. So this is the main one. It multiplies the utilization rate with the EV adoption percentage of the area. So it is not just telling you where the chargers are busy, it is telling you where the structural problem is actually the worst. High EVs, high congestion, not enough chargers. That area gets the highest score. And the third one is chargers to EV ratio. Total charges divided by the registered EVs per district. Lower ratio means higher risk. And finally, a grid vulnerability index. So broken plugs divided by total plugs. So this catches maintenance problems before they cause full station failures. Airflow is handling everything automatically. So through two separate pipelines. One DAG, a EV live telemetry DAG. So fires every 30 minutes, four tasks in sequence. Task 1, PySpark extracts and flattens TomTom data. Task 2, BigQuery loads it into the bronze table. Task 3, DBT builds the gold mart. Task 4, DBT runs schema validation. Tests to check data quality. Each task only starts if the previous one passed. All four green, one full cycle completed successfully. And the second tag, EV static dimension tag, runs once every 3 months. It loads the NetZA and KBA data. Before I wrote any transformation code, the first thing I did was properly analyze all the three data sources, and I found four specific reasons. One is NetZA was storing postal codes as numbers, so this was breaking all the location based joins. And another problem was KPA district names were formal names like Statkreis Hulm, but TomTom was just saying Ulum, so matching these two data sets was completely failing. And the another main problem was around 12% of the TomTom records has no postal code at all. So those stations are kept in the system but cannot be used for scoring because we cannot place them geographically. And finally, the fourth problem was KBA data was using European decimal format, comma instead of period. So 3.54 was written as 3 comma 4, breaking all the numerical calculation. So every problem I found, I built a specific fix for it inside the silver layer DBT models, looking at the raw data first, find the problems, then build the solution. So now let me show you the whole thing running live. Before jumping into the live demo, I wanted to show how the structure looks like. So first one is the buckets. In the buckets I have two folders. One is staged imports, that is for the live data from the TomTom, and another one is the static sources, that's for the static data sources for NetZA and KBA. And coming into the BigQuery, so the folders, the tables are raw NetZA, so I have given the name as raw for all these three. And the mart demand gap analysis, as you can see here. So these are the main columns. After transformation we will get, one is the current utilization rate, the allocation demand gap score, and charge to EV ratio, and the real-time grid vulnerability index. So first let me show you that this is actually running on the cloud and not on my local machine. So this is the Google Cloud Compute Engine page. You can see that VM here, so the EV pipeline orchestrator, the E2 medium, and it's showing green here. So now before I even trigger anything, I want to show you something important. This is the grid view you can see here. So all the green lines indicate that our pipeline has ran without any error. So data fetching has been got an error. The reason why here is the API failed, because since there is a limit in my API, I was not able to fetch more than 8 to 9 times a day. Since I am keeping my data to fetch for every 30 minutes, so it's getting exhausted. And in the graph view, you can see the four task chain. First one is the PySpark extraction, BigQuery bronze load, DBT gold mart build, DBT schema tests. Each task only starts if the previous one passed. So now let's trigger it now so you can watch the whole thing run live. So for the first time we need to trigger it. So let it get triggered now. So before that I wanted to show you how much rows are present in our data sources before, and then we'll show this. So if I run this, you can see that there are total 70,809 total rows now. So that's the PySpark hitting the TomTom API, pulling the live charging station data for all the 6 cities, flattening the nested JSON response in memory, and streaming it up to Google Cloud Storage as CSV file. All 4 tasks green. One full pipeline cycle is completed. Here nothing is manual. So for the next 30 minutes we will see another fetch data. So yeah, if I want to show you how the data is it fetching for every 30 minutes, you can see here this is the previous one that worked. So this fetched the data at 11 o'clock and this at 11:30 did all the operations and stored the data in the demand gap analysis, and this is at 12. So you can clearly see that for every 30 minutes, as expected, data is uh, the pipeline is getting triggered automatically without anyone's involvement. Now let me show you how the DBT layer works in the DBT itself. So this, okay, now if I type dbtls, this is showing the execution order that DBT resolved automatically before running anything. So you can see the MUT demand analysis model comes first, then the 3 validation tests come after. DBT figured out this order by itself uh, from the dependency graph, so I did not hard code any sequence here. So now again back in the BigQuery, so let me show you what landed in the bronze table after that run. So row count is now 71,462. It was almost 7,068 before I triggered the DAG. So the pipeline added exactly that many new rows in this cycle, and look at the days of data. That number is telling you how many different days data has been landing in this table. The pipeline has been running continuously for that many days. Latest record timestamp matches this session exactly, as you can see here, the timings as well. So now if I query the freshest rows ordered by the ingestion timestamp, descending this, top rows are timestamps from just a couple of minutes ago. Real station names, real German cities, real plug counts, how many are occupied, how many are available, how many are broken. This is actual live TomTom data that just landed. This I've considered only the top 10. And this query is very important. So this is the join L check. It's telling me what percentage of MART records successfully joined to NETSA and what percentage joined to KBA. So NETSA join rate percentage of 80% means that many stations got matched to the NETSA charger registry and we have grid capacity data for them. KBA join rate of 100% means that many stations get matched to the vehicle registration district data. For the stations where both joins work, the full grid vulnerability index is calculated. For the rest, it defaults to 0, which is a correct behavior, not a silent wrong number. So now let's go into the business questions. So I mainly have 3 business questions, right? So okay, so now I want to show you what is pipeline is actually useful for in the real world. 3 business questions that this data can answer directly. So the first question, so where should the next EV charger be built? This query is filtering only the postal zones where average utilization is above 70%, meaning the chargers, there are consistently congested and then ranking them by demand pressure score. So top row here, these are the zones with the highest congestion, highest EV density from KBA data, and the lowest number of chargers per 100 EVs. You can see that here. So in the Frankfurt, we need more charging points because there are more EV cars in the Frankfurt, but very less charging stations. So going to the next business question is that which grid zones are actually at risk of overloading. So this is different from the first question. High utilization just means chargers are busy, but grid vulnerability is combining 3 things together. How many EVs are registered in the district from KBA? What is the total power capacity in kilowatts at the chargers Therefore, they are from Brenta. And what is the live occupancy rate from the TomTom right now? So look at the top rows. Average grid vulnerability index is the highest. That means these zones have a lot of EVs, not much grid capacity, and charges are already running out. If there is a demand spike, could be cold weather causing faster battery drain, could be a big public event, these zones could genuinely get overwhelmed. This is not just useful for charging operators, this is kind of a signal that utility companies and city energy planners need to prepare the grid infrastructure in advance. Back to the final business problem. Is Germany's charging network actually keeping up with how fast people are buying EVs? So this is a macro level question. So cities ranked by EV adoption percentage from the KBA registration data, and next to that charges per 100 EVs. In a healthy market, that ratio should stay stable as adoption grows. More EVs, more chargers being built at the same pace. But look at the cities where EV adoption is highest. The chargers per 100 EVs number there is the lowest. That means that infrastructure is failing behind the adoption curve. In exactly the cities where demand is growing fastest, this is not a problem you can see tomorrow. It builds slowly over months, but by the time it becomes visible, it to drivers as long waiting times and unavailable chargers, it's already too late to fix quickly. And finally, you can still see that my data is fetching it properly. It started at 11 and again 11:30, 12, 12:30, 1. So to wrap up, what you just watched was a one full pipeline cycle running live from start to finish. TomTom API data came in through PySpark, landed in GCS, got loaded into BigQuery Bronze, DBT transformed it into the gold mart, schema test validated the output, and the three real business questions got answered from the result. That's it for the project, and thank you for watching. Dashboard part. So I've built mainly two dashboards. So one dashboard is for the EV charging operator and another one for the EV charging manufacturer. So before diving into it, so I'm going to tell what's the main problem. So Germany's EV charging operators are burning out a lot of money which they are not at all aware of. Uh, So code mainly contains two things. One is whether a station is busy or whether it's not busy. But the issue comes only when there is a more load system. So what happens when there is a more load is two things happens. One is the charging speed gets reduced. Why? Because if they don't reduce the charging speed, it gets heated up. So due to this, what happens? People wait for a long period of time, so the queue gets increased. Many people has to wait because the speed is low. The charging also gets low, and what happens is people get frustrated, due to which many of them would go to the other operators as well. So what this happens is this may leads to two things. One is intelligence command center. So uh, this is mainly built for EV charging operators. VP. So since he can't goes to BigQuery, fetch data, and see the numbers and understand, so he need a visualization where he can understand everything by just seeing. So that's what I built for him. So his main goal is he will just see what is broken right now and what changes that can be made and which workers can be sent, whether the issue may be with the cooling system or with the network connectivity, or uh, it may be with the power delivery grid as well. So by knowing out, he can send people there, and also the revenue that would be lost in the upcoming days. That's example. See, uh, now if they take the chance and send the workers there, the charging stations would work fine. But if they forget that and they leave, let it go, that would leads to a big loss where companies' charging stations would get destroyed and they will lose many people. So yeah, and this is what the three things is the charging owner does it. So yeah, and then coming to this dashboard, uh, we have mainly classified, and at stake it can happen two main things. One is what happens if the audience accept this. What happens if the audience accepts this, and what happens if it doesn't accept it? So if the audience accepts it, that is the VP operator. So what happens is, so we can save the revenue that would be causing a bigger loss in the upcoming days that could be solved, and also this is the main thing. Okay, and if he did not agree to it, a user revenue would be the main issue that he can cause in the upcoming days. So coming back to the dashboard, so I've designed a dashboard mainly in such a way that it contains it is going to tell you uh, 4 main things. One is what is happening right now, where it is happening, at what time it is happening, and what is the main reason for it, and where does an VP send workers to make the changes for it. So coming to the first one, the network L score. So network L score. So right now we have a 75 out of 100. So this we calculated this network L score mainly on with the help of 4 key matrices. One is the total revenue, the sum of the revenue added with the grid capacity. What's the capacity of a grid of one station, along with two main things. One is the uh, average demand gap score, and how much people are waiting in a queue. So combining all these four, we have got the infrastructure score. So right now we have a score of 75 out of 100. So this is that it's in a warning zone. I mean, not that much to worry, or it's in an orange zone, not that much to worry. So, but the key trend is it may get worse in the upcoming days. We have to watch it carefully and then try to fix the issues. And coming back to the sites in acute distress. So among 600 to 700 stations present right now, there are more than 82 charging stations that are in seeking for an immediate action. So it may be any issue in the cooling system or maybe network, but there are 82 charging stations where the company needs to look in and make the changes, otherwise the revenue would be even more loss in the upcoming days. And coming to the revenue, so 14 million euros, it's not a smaller number. So this much money is being falling into a place where they should think of it, otherwise that would be a add-on to the upcoming uh, days, and it would be bigger money for a company like charging. So sites, yeah, how I calculated the sites in acute distress is mainly with help of a map signal rule. So this contains revenue risk. Revenue is calculated based on grid capacity and current utilization rate and average grid capacity. So 288 kilowatts is the average grid capacity of one charging station. So this is very important to know, because so the more more the grid has the capacity, the charging first increases. So this all comes under what's happening right now. And coming to where it's happening, so I've classified mainly into 6. So this dashboard is done mainly with help of 6 European cities, basically 6 commercial cities in Germany, 6 economical cities in Germany: Cologne, Hamburg, Berlin, Frankfurt, Stuttgart, and Munich. So right now we can see that Cologne, Munich are the two cities where we need to have an immediate action to be taken. In that, Munich is the one which is our priority. Why Munich is a priority? Because you may figuring it out that the size of the circle is in the Munich is bigger. It means that there are more stations. No, that's not the real thing. So this is mainly due to of how much revenue it is generating. Even though Cologne is also in critical state, we need to first concentrate on Munich, because this is the key spot where we are getting more revenue. And when we click at the Munich, it will show us the top 5 postal codes that we need to concentrate. Because that was a in the Munich, these are the one which is generating more revenue, and we should concentrate on that. And coming to what's the reason, so it is generously a cooling system fault that may be caused due to overload. So instead of sending workers without knowing uh, what's the main issue is a bigger problem. So that knowing what's the problem in a station and sending the expertise to solve this is an critical requirement. And then coming back to the dispatch. So based on the urgency score, we have created a table where which company, or I mean which station is at risk right now, which needs an immediate action. So you can, how this urgency score is calculated is with the help of number of people available, that is the number of people in the queue, plus the charging speed and how much revenue that is generating. Based on that, this urgency score. And this ENBW is the station name or the company where majority of them is in Munich, because this is the place where revenue has been generating more. So this is about the dashboard 1. So going to the second dashboard, this is purely built for the manufacturer, VP of the manufacturer. So there are 5,000 to 6,000 cars have been sold. EV cars are selling out in the German market right now, but the companies don't know where to place a charging station, because for the charging cars, the charging stations are very much required. So they don't know where to place that right now. So this helps them to figure out which place is immediately required the charging stations, so that they can place the charging stations there. So it's been classified into average allocation demand gap score. So this score, it means what's the demand and how much supply we have right now. So it's a 66%. This means that 66, so the demand for the is more, but the supply of the charging stations are quite 66% is still 40% is missing up. We need to figure it out. And then which there are only 11 zones that are postal codes, 11 zones which are more using charging stations. We need to concentrate on that putting, see whether there are more charging stations in that zone. If it's not there, we need to put more charging stations there. And also the average EV adoption percentage. So it's 3.51%. So still it's an emerging phase in Germany. So since the charging EV costs have been trending right now, so in the upcoming days this would be increased. So this, and then coming here, this tree map tells us which areas are the ones that we want to concentrate. So the one which is in the red color indicates these are the zones where people are using more EV cars. So we need to concentrate on the ones which are in red. And also these are the emerging people have started to use, but before going there we need to concentrate because they are available in the market right now. But for the blue color, this one postal codes, what we have to do is we need to make more promotions, advertisement there, so that when people get used to it. So this is what they need to do it. And coming to this, so this adoption rate tells us two things. Tells us main thing in that adoption rate, which is more priority for us. See, now there may be more charging cars and more EV cars, more EV cars, and there will be maybe more charging stations. So in that location, we don't want to put more charging stations right now. It is manageable. So this classifies the one. So this is priority. We need to show more places. We need to show more concentration. This we need to show more concentration. So coming to the heat map. So this based on this tells us what's the trend. What trend at 1 hour, how much cars, what's the demand in 1 o'clock, and what's the demand in 2 o'clock. All this information this gives us, and this is one of the waterfall model which you can see here on the top right. So this is one of the most important. So for charging stations, yeah, see, even charging companies, car companies can't produce every time. So we need to concentrate on the 80%. So with all the big players in the market right now, and we need to concentrate on them and so make a collaboration with them. So if we don't do that, maybe the competitive companies like BMW or Benz, so they would get collaboration with the EV charging operators, and they would make money. So you need to invest on a player who is unknown, and you need to bring him to the market. You need to promote him, and then that's a bigger issue, right? So finally, so this EV charging dashboard and the entire project, from data fetching, loading to BigQuery, and then doing DBT transformations, and then also loading it back to BigQuery, and then using the Airflow. Finally, we have two main reasons. One is the charging operators are burning out more money, how to reduce their money and increase the trust in the people, and the loyalty. Also, if we increase the trust, the loyalty, the customers also increases. And also, which locations where we need to have more charging stations, so that people feel that charging cars are available in the market and even the stations are available, so that there would be no problem in the upcoming days. So yeah, that's it. This is about the entire project of the EV manufacturer, of the EV electric vehicles infrastructure pipeline. Thank you. Yeah, but